Today is Monday, October 11th. It's feeling like fall now. It feels cold and loud. I got my hoodie on, new hoodie, plaster hoodie, feeling cozy. And we're going to start learning about cyclohexane chair conformations. And here's a little picture of one that I had a former honor students drew up. And this will make more sense as we go over it today. And this is from our mechanism database, which it's a website I started creating years ago on Google. It was a Google Sites. And after years and years of me saying, no, I don't want to update the site because I didn't want to figure out how to use the new site, it finally forced me to update the site. And when it did, it seems like a lot of my links are kind of messed up. So if you, or when you come across a bad link, let me know. It's not going to be like an extra credit thing for finding an error, because it's like, I don't think it's my error, and it might be that it's like just a lot of bad links. So, but if you find one like, oh, I was looking at this problem, can you help me with it? Let me know, please. And there's some helpful stuff in this mechanism database. It's something that it doesn't have a lot of material for us yet, but it will as we go through more chapters. And cyclohexanes, which we'll learn about today, they're everywhere. So like, here's the fellowship of the cyclohexanes, kind of making here's another one, a coffee cup with that. It's making a reference to Lord of the Rings. So the internet has everything. You're not alone. So even if you feel like, oh, I'm really into this certain art or TV show or whatever, or music, and you feel like no one in your town likes that, you can go on the internet and find thousands of people just like you. It's kind of nice. Interesting times. So today we let's see, click here. So we'll do chapter 4, cycloalkanes today, like mainly cyclohexane like this. And then we might even start chapter 5. I don't know if we will. We'll see. Chapter 5 is stereochemistry. I started to make a Google slide with entrance and exit questions from our lab period. So I don't have everyone from the earlier part of the semester, but the most recent ones are there. So if you say, forgot to write down the exit question or entrance question, or maybe you typed it down wrong or something, or maybe I made an error in the first time I wrote it and then you're looking at it and this doesn't seem right, I probably have the corrected version here. So, and I'll try to remember to keep adding pictures to this Google slide. Okay, and then the schedule is up for spring of 2021, actually 2022. Whew, whole another year, 2022. And we'll have 3 lab sections again, but now we're going to be meeting on campus for lecture, room 101 for lecture, and in lab is the same as this semester. And when you go to sign up for these, some of you might have conflicts, like I think if you take botany and you take, if you take a hybrid botany, you're okay, but if you take the full on ground botany, it overlaps 2 of my lab sections, these 2 with the Tuesday, Thursdays. And that's not great, because then you only can add this one. And so when you try to add that one, it might be full because there's only so many spots. But don't worry about that if that's the case. Try to make it work out where you can get in one. But I will always add anyone who passes this semester. Whoever passes 12A this semester, I will get you in a 12B section next semester if you want it. I won't like say, oh, sorry, you got to wait another year to finish off your organic. No, I'm going to keep you going. So I can like give you an ad code for one of these and we work it out, all the math of it. Like sometimes, yeah, we can talk about it next semester. Hopefully it's not an issue. We'll see how it goes. Most spring semesters, I have like too many people wanting the Monday, Wednesday lab section and not enough here. So we work it out. Also though, knowing that, okay, if I pass 12A, I don't have to worry about like I'm gonna get into a 12B section. That's nice to know, but that doesn't mean don't sign up for a 12B section. Let's say you're like, oh yeah, I want this one, but and I could take this one, but I don't want to sign up for it. I'll just get the ad code later. Don't do that, because if you do that, that leaves openings for our lab sections for students from other campuses like ARC or Sac City or Folsom. And we don't want them to add into our lab sections because they're different, and different is wrong. I want those Sac City students in our class. Just kidding. Not at all like that. The only reason why I don't want too many openings and for too many students to come from other schools is it's not that they're different and they're wrong. I would like to meet more different people, but it's because they might have a real hard time taking 12B from me if they haven't had 12A, because in 12A I do things pretty different than most. So when they would come, I usually have 1 or 2 students every 12B session that didn't take me for 12A, and it doesn't fare well for most of them because they've like maybe not even gone over spectroscopy yet. And I spend a lot of time in the first semester on spectroscopy. Some professors, say the majority, don't talk about spectroscopy until the 12B. So that kind of puts them behind, and just other my details. So, but I'd say out of all the students I've had take 12B, who've never taken 12A, maybe like 25% do well. And the other 75% are like, oh, this is too much. And then they have to drop or something. So I just don't want to put them in a bad situation. Okay, so study tips. I had an email from one of you about study tips. So they were looking for practice problems. So I made up this list of the best practice problems, I think. I think the best practice problems are all other lecture examples. So what you do is you just, when you get the lecture example, you look at the original question, and then don't look at the answer to it. Try to work it out, and then look and check yourself. This is what I think of as like positive, making progress studying. A problem students run into sometimes is they'll get a practice problem that they don't know the answer to, and they'll spend a lot of time just like guessing, but they're not making any progress. And they would make a lot more progress if they just went back to the lecture ones with the answer keys. And then, the thing that'll really help you is if you try to make up a similar problem. Like if I have a bromination of propane and you make up one like a bromination of butane. It's pretty similar, but a little different. You make up your own problems like this and practice them. It makes you really good. It puts your brain in another like higher order of thinking, trying to make up your own problems. And if you can't do this, making up your own problems, ask for help. I'll help you with it. And then also the more you do it, the better you get at it. And it just makes all your studying a lot easier. Like I did this a lot. I kind of figured this out. Like I was taking biochem. Maybe I did a little no chem, but when I started taking biochem and doing this, I felt like I could spend half as much time studying for biochem as I did for general chem, and still get an A grade. So it was nice and learn a lot. All right, so then repeat these steps. Practice the problems already worked out, and then make up your own. Do that for office hour jams, because on the office hour jams I got a lot of practice problems. And even better, actually, the best problems to do are to come to office hours and do them in front of me, because then I can help you right away. And then entrance and exit questions are good to work on. And then after you've done this, then you're like pretty good with the material. That's when you do the homework. A lot of times students skip to the homework before they really go over the lectures, and then they just struggle with the homework problems. They're like, they don't know how to do it. And then other problems online are good. I've got these old honors practice problems. I just noticed all their links are broken. So I have to figure out what to do with that. I just have a lot on my plate. So, and then you could do textbook problems and other online problems as well. And notice I have you start with problems that have keys. Yeah, I think this is like positive studying. Also, make up your own problems is really a study booster. It'll make you much smarter. Okay, so you can do lab work as always. And I changed the times up a little bit. I said to like Monday, Wednesday, today. I used to say come in at 1:30. I think 1's okay. Come from like 1 to 1:50. Be all cleaned up if you have chemicals out, but before 2 o'clock, so that the other lab doesn't have to come in with goggles, and they can do quizzes and things. And then Tuesday, Thursday, 9 to 10:35. Come on by, do some extra lab work if you want, NMR, whatever experiment. And then the new extra credit assignment I mentioned before, I'll mention again. You can do your IR, NMR unknowns, ask me for them, and I'll get you some extra credit. You can get up to 6 points because you can do it 3 times. And then determination of unknown structures. The full assignment is due then, but I'm already getting them turned in. I think everyone has their spectra they need for this. So label them up, turn them in. And then solubility of organic compounds. That's not this Friday, that was last Friday. So turn that in if you haven't already. That one's getting late. Homework B, that was last week, it's late now, turn it in. NMR and IR spectra labeling. So I have an obvious quiz where, I give you the quiz ahead of time and the answer key. And that's today and tomorrow in lab. So, study, practice that, get full points on it. And then the homework C, I'll let you know when that's due after we finish chapter 4, which we're starting today. And then extraction of organic compounds. This weekend was what I was working on. I was working on this, updating it for you guys. And I'm not quite done with it. I'm almost done. I'm at the very end of it. But I want you to pre-lab it. So go through about as much as you can, an hour and a half or more by Wednesday, Thursday. And this will be, I don't think you'll get to the point where you're at, where I'm at my progress. And I want to finish up the last part of it today too. All right. And then exam 1 is in a couple of weeks. So start studying already. That's the schedule. Oh, actually, you know what? I should click on that add. We are in week 8 already. Whew. Okay, and then I mentioned this before. I'd updated that solubility of organic compounds question. And I mentioned this before, I mentioned again, if you spill any little bit of solid, clean it up right away. Otherwise you send the message to everybody else that that's what should be happening. And make donations. I've gotten some, but I don't think we've gotten, I don't know if I've gotten a lot actually, because they might have been right to Winstead, but let's try to make donations, help people out. And yeah, Coates's running that, president of the Black Student Union. Nice. And then make donations. Yep, get extra credit points, lots of karma points. And join any Sierra College club, get some extra credit, let me know. And honor students GSAs. I'm starting to get through these. Honor students, sorry, I've been busy with the extraction of organic compounds for a while. And so I haven't done a lot of these, but I got through Oleanas and it came out really good. I like the theme she chose. I'll let you all see this and I'll show you where you can find these. So actually, I'll close it out there. So if you come to our, organic step-by-step and you go to animations, and then in animations, this is sheet 1. These are all the animations I've made. I need to add some more too. Yeah, I got another one to add there. But if you go from sheet 1 to sheet 2, you'll see we got a bunch of them from last year, and now I've gone through Oleana, so hers is here. Let's check it out real quick. So in this one, it's just setting up the initial Newman, and she's doing it with an Ant-Man theme. Uh-oh, looks like I'm back in the quantum realm. All I need to get out of this is to pass through that molecule. And she's got one, wait. To escape the quantum realm, Ant-Man needs to draw Newman projections of the molecule hexane as his map. Wait, Newman projections of the molecule hexane. Okay. Luckily, he took OChem on his way to becoming an engineer avenger. So first, I'm going to number my carbons. Oh, and then Oleana, you'll notice I've updated this a bit. I started to fix a few things, and then I started fixing more and more. But that's what's taken me so long. Next, I want to enter through carbon 3 and exit through carbon 2. So it's going to go through there. I need to be mindful of the secret hydrogens. I'll give them color: purple, blue, yellow, green. Now I'm going to draw the Newman projections. This first carbon is the dot. The second carbon, 2, is the big circle in the back. Now to draw the bonds. So I'm going to go through it faster, and then you can go through it slower. Pretty cool, right? Not bad. Staggered conformation. Wow, I made it out of the quantum realm. It pays to learn OChem. Ant-Man and Newman projections coming to a theater near you. All right, so there'll be more of these. I have, I think, 5 more of these to go through, and then I'll have other topics in the future too. So these are other things that can help you study this year. Okay. Any questions about the outline for today? Okay, I'm going to go ahead and start with the Jamboard. Today's lecture. And I was thinking I was going to go right into cyclohexanes. Then I thought, wait, you know what? let me do one more reaction coordinate diagram that includes Hammond postulate, but it's not the what's it called? Not a radical halogenation, but another polar reaction mechanism. So let's do that. Okay, here we go. I'm going to do this one here. I like this one. I'm going to take this alcohol, have it react with, let's go H hydroiodic acid. I'll make it colorful too, why not? So the first step of the mechanism is the alcohol gets protonated. It's been a little while since you've seen a polar reaction mechanism in which the curved arrows have double, like a full-headed arrow, not the half arrows, right? Nice, huh? And so we get the protonated alcohol and iodide in the first step. And this step is exothermic. I would hope you can predict that, because I'd hope you predict this is more acidic than that. This guy's pK is about -2. This is below HCl, which is -7. So it's even lower than -7. Okay, and then the second step is the rate determining step. In which this newly formed iodide is this is actually, we talked about this earlier, this iodide's a nucleophile. It's nucleus loving, it loves positive charge. This carbon has a partial positive charge because of the oxygen attached to it. And so that this is my nucleophile, this is my electrophile. And we get the following. Oh, I don't want to do it that way. I keep wanting to draw that last bond red. Oh, I still want to do it. Okay, stop. All right. Oh, nope, redo. I want this to be blue. There we go. Oh, goodness, why did I hit that? There we go. And we also make water. There we go. Okay, two-step reaction. The second step is exothermic as well. And rate determining. And the overall reaction, I'll actually write this is the mechanism, right? I usually do the overall reaction above, but I'm going to do it below. So the overall reaction. Oh, that was sloppy, huh? It is also exothermic. I think I didn't even have to tell you that though, huh? Because if the first step's exo and the second step's exo, of course it's exo. Now the overall reaction will be the alcohol reacting with the HI, the hydroiodic acid, to produce the iodine and water. So you can see the overall reaction eliminates the I- intermediate and the protonated alcohol intermediate, like they just like cancel each other out. These two make those two. Okay. Now I will. I'm I'm going to duplicate this and I'm going to shrink that down to draw my reaction coordinate diagram with Hammond postulate considerations. Okay, switch over for you as well. So can I select everybody? Oh, come on, come on, come on. No, it keeps canceling out at the side of the screen. I might have to do this differently. Oh, I got it. Shh. Okay. It just got a little bit funky. What did it lose? It lost a little bit up here. I got to erase that. But I think it's all right. Whoop. There. Come on, buddy. Ooh, it's going to be nice to be at a whiteboard next semester. Just draw this out. As much as I like Jamboards, Jamboards are pretty awesome, but still can be frustrating. All right, here we go. Energy. Reaction coordinate. I'm going to start up high in energy because I know it's going to be all exo. Exo. This first step, exothermic, boom. Produce our protonated alcohol and the iodide. Transition state. Activation energy starts there. Next up, exothermic as well, and the overall reaction is exothermic, which will happen automatically. Now, why did I, did you notice I did something special with this? What did I do? I was careful to do. What do you see here with this second step? Well, how's it different from the first step? Can anyone tell me what I did? Oh, I see it here in the chat. Made the reaction, the rate determining step bigger. Not bigger, but made the energy is greater, showing that the rate is low, better wording. I made sure that you're on the right track. This activation energy has to be longer than that one. So this takes more energy to overcome and get to this transition state. So it's going to be a slower step. So yeah, that's definitely my rate determining step. I made it bigger. And this reaction is overall exothermic. Nice. Okay. So now I set all this up just to show you some transition states with the Hammond postulate and with polar reactions, because we've only done radical reactions so far, huh? Okay, so this first step, what does this transition state look more like? Does it look more like reactants or does it look more like products? Well, the transition state is closer in energy to reactants. It's much further than products, much closer than products. So it looks more like reactants. So that means I have to, did some of my thing get erased? What happened here? This guy is annoying. I gotta reload my page. I don't know what's going on. Yeah, it seems like, yeah, this got erased, huh? Okay, I'll fix it. Okay, let me just do it this way. I'll go back here. I just screen captured it. I thought I'd try the other way. It wasn't a good idea. All right, yeah, that's what I want. Boom. Okay, so that first step, you can see the first step in the mechanism is the oxygen of the alcohol is reaching out to deprotonate the hydroiodic acid. So it's going to look more like reactants. So that bond is just going to be forming. So I'm going to exaggerate it. I'm going to draw it super long. And then the proton is here. That's being reacted. And then the HI bond, it's really short because it's only just beginning to break. Okay, so, but there's one other thing we need to talk about that we didn't have to discuss for radical halogenations. We got to talk about the partial charges. So the oxygen starts off at what partial charge? Does it start off at 0, -1, 0, or +1? Starts off at 0. And then it goes to +1, right? And is my transition state closer to 0 or is it closer to +1? See, the oxygen went from 0 to +1. The transition state's actually closer to 0 because it looks like reactants more. So for that transition state, I don't know the exact number for it, but I'm going to say it's at like +1/4, say. It's not quite to +1/2. And then this would be right here would be +1/2. Since I don't actually know it's +1/4, I just know it's less than 1/2. I could say, I could go also, or I could say like delta plus. It's just delta plus, but then on the iodine, now for it, what's its number line look like? It starts off at what is it? Is it -1, +1, or 0? Where does it start? Iodine starts off as 0 and becomes -1. So it starts off over here at 0 and it's going towards -1. But what does its transition state look like? Transition state is right here. It's closer to 0. It looks more like reactants. So it is only going to be like -1/4. Or just like delta minus. The delta, say if I just put delta plus and delta minus, it's not telling you as much, huh? But I don't know that it is -1/4. It might be -1/3. I don't know exactly what it is. So I'm kind of in a quandary, but I want you to try to do these fractions. I think if you can understand those, you're really getting this stuff. Okay, so that's transition state 1. Didn't I say transition state 1 equals this at some point? I don't know. So let me shrink that down, make some room for the other one. So that's the value for that guy. I'll put oxygen of transition state 1. Okay, so let's now try to work on transition state 2. So in this one, we have the iodine making a bond to the carbon. Oh, but first off, does this transition state 2, does it look more like reactants or products? Looks like reactants to me. So that means this iodide is just beginning to form its bond. It's a long ... to it. And the bond to the oxygen is only just beginning to break. Okay, looking more like reactants. Now about the charges. So the iodide here, let's go -1, 0, +1. Okay, what is it starting off at? What charge? It's starting at -1, and it's going from being -1 to 0 charge. So it's going this way. And its transition state is reactant-like, so it's going to be over closer to -1. So for this one, I could say something like, oh, it's going to be -3/4 or delta, oops. Or delta, oh my goodness. Delta minus, like a lot of minus. The oxygen, on the other hand, it starts off at what charge? Starts off at +1 and ends up at 0. So starting off +1, it's going towards 0, but it's closer to +1, right? Because it's reactant-like. So it's going to be closer to +1. It's going to be like +3/4 or delta plus, like a lot of plus, huh? Okay, we got it. So we did something we learned prior to learning about Hammond postulates. So Ryan was asking a question on the chat. Ryan, what's going on here is, think about it this way. In the mechanism over in the upper left, Ryan, at the start of the reaction, the carbon to oxygen bond is fully formed really short. At the end of the reaction, the bond between carbon and oxygen is completely broken super far. This water can be infinity away, basically. Infinity picometers away or whatever. So it's close to start, it's far to finish. So the transition state looks like the start. So it should be short. And then the iodine bond, initially the iodine's super far from the carbon. So it should be far. So pretty sure I did this one right. I can mix those up though. Hope I did. Okay. So yeah, as I was saying, we've done Hammond postulates for radical halogenations. Now we've done it for polars. So now we can use them all the time. Now, when I say polars, I mean mechanisms that use a pair of electrons. All right. Chapter 4. Here we go. Chapter outcomes. Wait, sorry. I'm at chapter 4 here. Okay. So we'll start off with some nomenclature. I have I have some chapter 4. I have a chapter 4 outline, chapter outline. I may do a little bit of this, yeah, just to get through the beginning parts real quick here. Yeah, I'll do it. but actually this makes me think, before I do that, I had one other thing I noticed earlier. I was like, oh, I'll show that. Not that. Where did that go? From an old outline, this is the one. Oh yeah, just a little quick reminder about in lab. I'm gonna have you weigh out things a lot of times on scratch paper, but if you set the piece of scratch paper on the scale in this manner, you're gonna get a false reading because the paper is resting on this outer ring, not on the balance pan. So you want your piece of scratch paper or whatever you're using to only touch the balance pan in the middle, not the outer ring, because then it won't give you the right mass. Okay. Then, so Ryan, did I answer your question well? I still see your question up there, but I'm not sure if it's going well.
I'm not sure because I thought that since it's closer to transition state, or since it's closer to reactants and transition state too, I thought that the bond would be, like the bond line would be longer for the water to the carbon, just to show that it's staying in that like configuration instead of being attached to the iodine.
Yeah,
And
actually,
you have it where it's reversed.
yeah, it is correct the way it is. But remind me of this question when you come into lab, and we'll get you straight.
Okay.
Yeah. And then chapter 4. So chapter 4, it's about cycloalkanes in general. Like this is a cyclopentane, this is cyclohexane. But you're going to see, we're going to focus mainly on cyclohexane. Cyclohexanes are the main ones. So we'll do a little nomenclature first. We learned how to name alkanes already. Cyclohexanes are pretty similar. So this one here is 1-chloral, 2-ethyl, 1-chloral, 2-ethyl, 4-propyl cyclopentane. So what's going on with all that? Let me actually name the other two. Put them on the Jamboard, it'll be easier to see. Too many things going on here. So on exam 2, you'll have a cycloalkane nomenclature question, I'm pretty sure. Because I usually just have like the first question in exam, some kind of nomenclature question. And I don't think we'll get any other nomenclature before exam 2. So yeah, it'll be this. So how's this numbering work? And let's try to figure it out. It looks like carbon, the chlorine was labeled carbon 1 there, and 2, 3, 4, 5. So why do you think the chlorine got 1 and the ethyl 2, 3, 4, 5? Why didn't we go clockwise, like 1, 2, 3, 4, 5 that way? Let's draw that out and think about it. So why not 1, 2, 3, 4, 5? Having a 1-chloro, 3-propyl, and a 5-ethyl. Why not do that? Does anybody have a guess at why that didn't happen? Yeah. James has the right idea. It's more about the numbers on this one. You want to number the groups in a way that gives you the lowest possible numbers. After that, then you would go alphabetically, put the alphabetical one first. Yeah, these are higher numbers. So, because we have a 1, 2, 4 versus a 1, 3, 5. Okay, and then why chloral first? Sorry, chloral, but chloral before ethyl before propyl. That's alphabetical. Okay. And then over here, we start with the chlorine, 1, 2, 3, 4, 5, 6. And we could have gone, though, gone the other way. We could have said, oh, let's go from chlorine around 1, 2, 3, 4, 5, 6. So both ways would give you 1, 4, huh? So why did we go with bromine as 1 and chlorine as 4? That's the alphabetical. If numbering around the ring gives you the lowest numbers 2 ways, you go with the alphabetical. Okay, and then you'll see that I have, they're both 1-bromo-4 cyclohexanes, but they're different molecules, huh? This one is called trans here, and this one is called cis. So trans means they're on the opposite side of the ring, and cis means they're on the same side of the ring. Type that one in. Trans is up. Side. Inside for cis, right? So these two molecules, they're actually called stereoisomers. We're going to discuss stereoisomers in greater detail next chapter, but I just figure I'll introduce it a little early now. So these two molecules, they have the same molecular formula, the same atom connectivity, like you have the bromine at 1 and the carbon at 4, chlorine at 4. But they differ in 3-dimensional arrangement. Like they're not the same molecules, because if I slide one on top of the other, they won't, all the atoms won't superimpose. They're not exactly the same. So they're stereoisomers, and these ones are called, these are diastereomers. We'll do more of that. That's just a preview. We'll do that more next semester, next chapter, not next semester. All right, so boom, boom, boom. Yeah, that's that stuff there. Yeah, that's a review. Here, I'll talk about some of this. Okay, I'll just copy it all. I did verbally some of that already. Okay, so isomers, different molecules, same molecular formula. And then constitutional isomers, same molecular formula, but different connectivity. Like, I'll give it to you here. Let my Jamboard catch up. Oh, come on, Jamboard. Let's go. So an example of this would be like if I have butane and 1-methylpropane. They're both C4H8, 9, 10, C4H10, but they're connected together differently. So they're definitely different molecules. And then this one is where you have same molecular formula, the stereoisomers, same molecular formula, same connectivity, but different 3-dimensional arrangements. So that's like the, let's go, I'll do another one like this, go. Fluorine. Ugh, that got pretty ugly. Say a dashed methyl right here versus dashed fluorine, dashed methyl. So this one is this first one cis or trans? This one's trans. The two groups are on opposite sides. And this one's cis, they're on the same side. So one way to name this one is got to come up with the numbers first. So what should come first, fluoral or methyl? Because I could number like 1, 2, 3, or I could go 1, 2, 3. I can have the fluorine be 1 or the methyl be 1, and I still just have the same low numbers. The fluoral is going to be number 1 because F comes before M in the alphabet. So this will be named trans 1 fluoro 2 methyl. And then don't go psycho and forget your cyclo. Propane. Seems like the most common mistake in these cycloalkanes is don't forget the cyclo part of the name. Don't go psycho and forget your cyclo. And if you do go psycho, know there's help out there. You know, we're trying to reduce the stigmatism of mental health issues. So get help. And that's why we're working so hard, right? As students, you work really hard to go through school, to go to the graduate school, to get the good job, the good house. And then all this pressure you put on yourself to get there, when it finally breaks you down and you have your breakdown, you have the money to afford to go get good help for your mental health. But hopefully along the way, you can do some mental health practices, exercise, eat well, take a break so you don't have to have the breakdown. But if you do, hopefully you have good insurance. You'll be good if you work hard. All right, so we got that one. Next one, the other one is going to be the same, except for it'll just have cis at the beginning. So this one is just going to be cis 1 fluoro 2 methyl cyclo. I don't want to go psycho and forget my cyclo. Propane. And these two guys are in they're stereoisomers. Oh, what the, my bad. There we go. They're both, they have the same molecular formula. They're both C3H H6, no, 3 C4H8F. Wait, am I right about that? 3, 4, 5, 6, 7. Oh no, 3, 4, 5, 6, 7. No, not H8, H7. Had anybody caught me? No. Okay, so yeah. So let's do this. Before I continue on in this, well, actually, let me finish this page really quick. So the degrees of unsaturation formula, we've already seen that, huh? That's just your degrees of unsaturation equal carbons +1 minus hydrogens plus halogens minus nitrogens all over 2. We've seen that lots of times. So that applies now because these rings we're going to be talking about introduce 1 degree of unsaturation. Here, let me make this neater. +1 minus all that. Okay. And it turns out the cycloalkanes, they have ring strain. So for instance, cyclopropane has a lot of ring strain. It doesn't want to be a 3-membered ring, those carbons want to have 109-degree angles, right? But they can't have that in a triangle. They want to be about 109 degrees tetrahedral, right? And I'll do there, but an equilateral triangle, right, has what bond angles? What has what angles? Is this an equilateral triangle? That's what it would be, right? How much each? 60 degrees, yep, because they have to add up to 180. So that's a lot tighter than 109, right? So they don't want to really be 60. So cyclopropane rings like this, they have ring strain, they kind of want to pop open. And they are present in nature though. And because of the ring strain, they have actually reactivity similar to an alkene. So they can, some of the reactions that alkenes undergo, cyclopropanes will undergo, and they'll pop open. Then when you go to a 4-membered ring, it's a little less strain, because now they're 90 instead of 60. Getting closer to 109. And then 5-membered rings get a lot better. We see a lot of 5-membered rings. So what is a 5-membered ring? Bond angle? Anybody know? Is it, I forget. I want to look up my calculator. I think it's 180 divided by 5 or 360. I should know this. I'm not good with my geometry stuff. I forgot all that stuff. Let's say 180 divided by 5. I think it's like, no, that doesn't look right. It's probably 360. 360 divided by 5. 72, is that right? I don't know. We call it a regular cyclopentane. 107. That number does sound right. I should say pentane, huh? Oh, pentagon. Wow, I can't think. What am I doing? 108. Okay. .108 degrees. So it's getting, oh, it's getting pretty close, huh? All right. There's more to it than that angle, though. We'll see. I wonder where the 108 comes from. Whenever I see these like proofs of these things, I'm like, oh, that's cool. But then, oh yeah, it comes from the interior angles. If they're all 72 times 5, then you need whatever is left over there. Yeah, those are good. Okay. So, but when it comes to these rings, I'm treating them as if they're completely flat, but they're not. Well, the 3-membered ring's flat and the 4 is pretty flat, but the 5, it puckers. It doesn't stay flat. So I'll show you cyclopentane. Pucker. puckers kind of like that. Actually, I'll put it on the next panel. So this one's cyclopentane. P-U-C-K, not flat. And the reason why it wants to pucker and not be flat is because if it's flat, it's all of its hydrogens will eclipse each other if we were looking down their Newmans. When they're eclipsed, you know, they have electron-electron repulsion, higher in energy. So in order to try to get to a lower energy, they pucker like that. Okay, we won't deal much with that. The ones we're going to deal with the most is cyclohexane, six-membered rings. So the cyclohexanes, they're like the main focus of this chapter because cyclohexanes can take on a chair conformation. That allows them to have 109-degree angles and all staggered interactions down their bonds. I'll define what a cyclohexane chair is and show you how it's all the bonds are staggered shortly. But I'm just setting it up now. And then the last thing is just a little fun fact. I thought about not even mentioning anymore. This is one of the annoyances I have with standardized testing. So it seems like when I used to give the ACS exam, there was always a question about like cycloalkanes having this weird thing where their boiling point is higher than you would expect compared to the linear alkanes. And I was just like, it's just a random factoid. So I would mention it so that my students, I want them to do really well in the ACS exam, but I don't teach to the ACS exam, but this is maybe one thing when I did. So it's a little bit interesting. Cycloalkanes have higher boiling points than linear alkanes. So if they're the same number of carbons, so like this is cyclohexane. It has 12 hydrogens and 6 hydrogens, 6 carbons, 12 hydrogens. And then N-hexane has 6 carbons, 14 hydrogens. So this is heavier. Normally a molecule is heavier, it has a higher boiling point, but not for the cyclo ones. And I think it has to do with the entropy of boiling, not the enthalpy, not like the bonding between the intermolecular interactions. It has to do with enthalpy. The N-hexane has more entropy, and we could talk about it if you're curious. It's an interesting thing, but all right. So now we're going to start the bulk of this chapter, drawing and understanding cyclohexanes. They're the key, the star of the show. I think I'll stop the screen share. Yeah, so I can see myself better. Yeah, this will be better. Okay, so let's start with just like a 3-membered ring initially. So if I try to make a 3-membered ring, oh, I feel like it's gonna break my bond. See how tight it is? Oh, so that's a 3-membered ring, a cyclopropane. You can see that's gonna be pretty high in energy due to this ring strain having to close on itself. And besides that, it's if you look down one of the bonds, you'll see for like a Newman projection, like say, oh, it's hard to do. It's like a backwards for me here. You can see how everything's eclipsing, huh? Let me hold it. Let me if I try this one. Yeah, there we go. See how like the hydrogens, the white hydrogens are eclipsing and the green hydrogens are eclipsing. So a 3-membered ring is pretty high in energy. Let's go to a 4-membered ring. Four-membered ring, still pretty high in energy because of the ring strain. It's at about 90 degrees when it wants to be 109. And if I look down, the Newmans, they're all going to be eclipsed, no staggards. Let's add on one more where it gets a lot better, but still not the best when we have a 5-membered ring. There we go, 5-membered ring, much better. It could take, if it's completely flat, the 5-membered ring, say I make it, see how it looks very flat to you. If I look down the bonds, everything's going to be eclipsed if I have it completely flat, all the hydrogens. So like this way. See how those ones are eclipsing down the line. But if you pucker it a little bit, I talked about the 5-member rings, they like to pucker a bit. They do that so that they'll be, some of them can be staggered. See how that's staggered? If I come this way, that one's pretty good. That looks staggered. And now it's getting pretty, it's like a skewed one. It gets close to eclipse, and like that's pretty close to eclipse. So the puckered can help some, but not all of them. But when we throw on a 6th carbon, that's when the magic happens. Now we've got, well, let me back it up. Let me say before the magic happens, let's just look at it flat. If I do the 6-membered rings completely flat, try to make it completely flat. And then I look down the Newmans, they're all pretty, they'll be, if I have it completely flat, they'll be completely eclipsing, high energy eclipsing. Right. But now I'm going to show you the new thing about cyclohexanes is they can become chair conformations. So what this is imagine a chair like on a at a beach pool, a beach or at a pool. I think these are more common at the pool, where you can like lower the feet, click, 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 you like click it, you go click, 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 and then you can raise the head, click, 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 like that. And then you go too far, and so you got to go all the way, click, 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 and then you got to go back, click, 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 till you get it just right. Click, 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 click. Oh, it's not quite right. Click, 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 click. Oh, just order me some nachos and a drink, and I'll relax and I'll get this way home. Okay, so just imagine we're on a vacation in our pool, in our chair at the resort. And so the chair conformation looks something like this. This is the head of the chair. This is the butt of the chair, this square area in the middle, and that's the feet of the chair. And when the cyclohexane takes on this chair conformation, then it results in all the bond angles are completely staggered. Isn't that nice? So see how that's staggered? I'll come down, look down this one. Oh, you're actually looking down 2 bond angles. You're looking down this one and this one. You can see they're both staggered. Pretty cool, huh? So the chair conformations add a lot of stability. And so because of that, they're lower in energy, and you find them a lot in nature. The cyclohexyl chair conformations are part of steroids. They're a part of carbohydrates like glucose. And so they're an important part of the world because of their energies. So we're going to learn how to draw these and interpret them. That's the bulk of this chapter. Let me show you. Let's practice. I want to see what I want to practice first. Drawing first. Let's just get to drawing them. So I'm going to draw some just really quickly. And don't try to like keep up with me. I'll slow down after I do a few, just to give you the idea of it. So here we go. I'll draw a flat cyclohexane first. This is a flat cyclohexane. And I'll number it around the ring to show that it is 6 carbons. So this is the flat cyclohexane.
Hey, Mark.
Yeah.
We can't see your screen if you wanted to be sharing it.
Oh, you're the best. Thank you. Share screen again. Perfect. Yeah, thanks. Okay, I'm back to the flat cyclohexane here. See how I numbered around the ring. And then I'm going to turn this into the chair conformation. So here we go. So I've drawn these a lot, so I've gotten decent at them. I can draw them pretty quickly. And I want you to get good at them too, but right now just watch. And I'm going to number my carbons the same way as I did before. I'm going to put the 1 over here and the 2 over there. Let me show you what I mean by this. So this 1 is the leftmost carbon, right? That's carbon 1. And I still have it as leftmost, right? Sounds like a rapper name for me, like leftmost def or something. So leftmost carbon. And then we got rightmost here. Carbon 4. So it should also be on the right, the furthest too. So this is 4. Yeah, that's my furthest right carbon, 5, 6. It really helps to do that, to number your carbons, number them consistently, and like have whatever's the leftmost carbon here is the leftmost one here. Right, you know. Okay, so this guy over here is called the foot of the chair, because it's, imagine a beach chair. I've actually got a nice picture of this. Let me go. It took me a while to find the chair I wanted, and I don't actually love this one I got, but I think it's this one. Yeah, this one. Oh. Oops. I gotta invert her. Oh, I don't think I can here. I thought I had that. Yeah, I needed it. Which one did I click on? I thought I clicked on the correct one. Isn't this one the correct one? Is it flipping when I paste it? It flipped, huh? Weird. Okay, then I'll pick the wrong one. Oh, I think it's because I know what's going on. It's because that's the original picture that I got, and I flipped it on this one, and it's keeping track of the original somehow. Boom, that's what I want. Oh, oh. So you see how this is the kind of chair we're trying to emulate here? And this is the foot of the chair. And this is the head. The head of the chair. And this is like the seat of the chair. So if I were to number like this guy, this chair, I would say this is like carbon 1 right there. And we got 2, 3 is back down in behind her, you know, and then 4, 5, 6 kind of thing. That's where the name comes from. Chemists think of it as like a chair. Okay. So let's look at me doing something with these chairs, and then we'll work on drawing them. But I just want you to get a good visual of them first. So I'm going to turn off my screen share again. Help remind me to turn it back on if I forget. Okay, here we go. I'm holding this up. I'm trying to hold it up like I've drawn the first chair I drew for you on the other page. There it is. I think that's pretty good, right? Do you agree? I got to tilt it this way. Okay, there's my chair. Does this look similar to the drawing I just drew for you? Except for now, I added all these hydrogens on here as well. Okay, there we go. So now what we're going to do next is something called a chair flip, but we probably shouldn't call it a chair flip, but everybody does, so I still do it that way. We should call it a chair flex, because a chair flip is when you it would seem like you flip the whole chair over, but that's not what it's meant to be. It's meant to be that a chair flip is where you take the foot of the chair and you flex it up, and then the head of the chair and you flex it down. So now you have the foot of the chair on the other side, the opposite side, and the head of the chair on the other side. So let me actually show you. This is a good thing to play with your models. Remember I said the model kits you don't use for a little while and then you use them again. These are good. If you play with your models, make up cyclohexane with your model and try to work at the flipping. We'll work at it in lab too. Get good at flipping it back and forth. It'll help you see some things. I made up a good, I started making a really nice chair flipping GSA, and it's actually pretty awesome, I think. I'm bragging, but I like it. I think it helps, but I still need to finish it. I have a couple more things, but I haven't done it yet. I still have to finish extraction of organic compounds too. But here we go. But before I do that, actually, I had an honor student. I'm forgetting his name. I got to add his name to this. I had him make up this one, and I think it's pretty good. This like a visualizing going from the flat to the chair conformation. So like if you have a flat cyclohexane, the way I imagine flat meaning like I'm looking at it from the top, so I don't see the chair nature of it. And then I numbered the carbons 1, 2, 3, 4, 5, 6. And that's the flat ring. Now let's make it into a chair and use a GIF to see it. Do you see how we're rotating the ring? So carbon 6 comes up in the front and then carbon 2
Mark.
is in the back. Yeah. Oh, I'm not sharing again.
You're not sharing. Yeah.
I hate that. Thank you so much. You're saving me a lot. Yeah, nachos. Okay. All right. So let me go back to the beginning of this. So, and I found this animation in this week's like assignment area right here. Visualizing chair, cyclohexane chair, flat chair visualization. All right, I go there. Present. Okay, so here it is. It's got carbon 1 labeled here, 2, 3, 4, 5, 6 around the ring. And then that's the flat. I'm looking at it from the top. And then I'm going to rotate this. This is how I want you to visualize it. Rotating it in a way where carbon 6 comes out in front and carbon 2 is going to the back and 3 is going to the back. 5's coming to the front. Kind of see it. And if I were to pause the rotation, like right, boom, that's how we draw the chair. This is what rotating to the point where it's going past where we draw it, you know. This is mainly just to show you how we come up with that chair conformation. And now there's another one I want to show you. So below that one is a longer one. Visualizing cyclohexane chair flips, flexes. It's this one. Present. So I think this one's pretty good. And I can start off with not just the cyclohexane alone. I start with a substituted cyclohexane. I don't know if I name it though, huh? I don't think I name it. I think I number it though. I think I'm numbering it. I'm not numbering it according to nomenclature. According to nomenclature, it should be bromine is 1, huh? 1, 2, 3, 4, 1 bromo, 4 chloro, 2 methyl cyclohexane. But let me just number this just for helping me draw the cyclohexane numbering. Yeah, I think I mentioned that too. Not IUPAC numbering, just helpful numbering. Okay, so this is equal to this guy. If you're holding it, if you make a model and you hold it looking down the top of it, right? And I can number those carbons again. And then I want you to visualize it this way, where you're flipping up those red carbons 6 and 5 towards you. See how they're coming towards us, the red ones? And then the carbons 2 and 3 are going to the back. And when we rotate it this way, the chlorine that's dashed back, this yellow one, becomes pointing downward in the chair. And then the methyl that's wedged up in our flat drawing becomes, it's still pointing up, but it's at an angle, huh? And then the bromine dashed back here is pointing down at an angle. Okay, so some key things to focus on. Oh, here I'm drawing the chair like that conformation. I'm going to number my carbons around the ring the same way as I did it here. And I'm going to remember that this was the leftmost carbon because it was the leftmost carbon up there, right? And this is the rightmost carbon because it was the rightmost carbon there. And then the I can add on my groups. I'll show you the bond angles and stuff of these shortly, but you should be able to see that for this guy, should I put the chlorine pointing down or up? Should right here, should the chlorine be the down position or the up position? Chlorine is down, yeah. James was asking about if I have a double bond in the ring. That's like a cyclohexene. There's a whole nother way to draw those, but we won't learn those. Those would be more for like a Chem 12C course. All right, so the chlorine's dashed away from you. Yeah, it's pointing down, as we can see in our GIF too. And then over here on carbon 3, I've got that methyl and a hydrogen. Which way does the methyl point, up or down? The methyl is up. Yep, good. And then carbon 4 has got that bromine. Is that bromine going to be pointing up or down on this one? Good, down. You got it. Okay. And then, so bonds pointing up are orange. I made those all orange. And the bonds pointing down, I made them all magenta. This is down, down, down. All right. And this has a chair flip. When you chair flip, you take the foot of the chair here, you bring it up. And you take the head of the chair on this side, bring it down. So, and then I put the heart here because I want everybody to give equilibrium love. For some reason, there's a lot to draw in these. People forget that to draw the equilibrium arrows between these, but there should be equilibrium arrows there. So give the equilibrium arrows some love. All right, and then carbon 1, it was the foot, and now it's the head. 2, 3, 4. 4 was the head of the chair, and now it's the foot. 5, 6. And leftmost still, rightmost still, just like carbon 1 was leftmost, still leftmost. Draw my two groups. So carbon 1, what should the chlorine be facing, up or down, do you think? Think the chlorine should still be down on this when we do this chair flip or flex? Should still be down. Doesn't change when you do. Like if you could see my, let's see if you can see me on this little panel here. Am I on? Am I on? There I am. I see. Yeah, yeah. So when I go from, I got to do everything backwards for you. Huh? So when I do a chair flip, like if this group green is up, when I chair flip, it's still up. All green still up. So right now, all white are down. When I do a chair flip, all white are still down.
Mark, we can't see you if you're showing something.
Oh yeah, it's not on the little box in the corner. Oh, maybe because I'm sharing my screen now. Oh, here, let me finish this slide then.
Oh, sorry, wait, I can see you, sorry.
That's okay. So thanks for all your help, Ryan. I really appreciate it. Okay, so here we go. So the methyl is also, it was up on 3. It's still up on 3. And then on carbon 4, that's one with the bromine. Should the bromine be up or down? What do you think? Bromine should still be down. And it is. There we go. All right. It turns out this one's lower in energy because this methyl is the largest group. I know bromines and chlorines could be pretty big atoms, but the methyl is larger because it has 3 hydrogens and a carbon. It's got 4 atoms versus just single atoms. So the methyl's largest, and it's in this, we call this an equatorial position. That means it's in less, it's less steric hindrance than in the what we call axial. I'll get to that shortly. So you'll see the low energy thing shortly. And then this is what I was saying. I want to add to this diagram, but I'll show you here visually. Let's see. Actually, I'll do this one first. Yeah, there we go. So here, I'm going to show you a couple of things. I need to animate this, what I'm about to show you live, but that's okay. We'll get there. Okay, so as I was saying before, and it was on the little screen, I'll make it on the big screen now. So I've got this cyclohexane. It's in a chair conformation. Right now, what color is pointing up? What color is all the up? This is up. This is up, 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 up. What color is pointing up? It's all green, huh? And then what's pointing down? All the white ones, huh? I'm going to do a chair flip and see what happens. So green's up, white's down, chair flip. That goes to the head, that goes to the foot. Here's the chair flip. So now what is, let me try to hold it cooler like that. Yeah, there we go. So now green was up. Is green still up? Yep, green's still up. White's still down. So doing a chair flip, whatever's up stays up, whatever's down stays down. They don't change. All right, so now there's another thing I want to talk about though. I want to talk about, these are called, there's different names for these positions. So the ones that are completely vertical, like this green one here, it's called axial. Axial. The ones that come out at an angle are called equatorial. So what I'm going to do is I'm going to change up my colors here a bit. I'm going to make all my greens axial and all my whites equatorial. Change. Okay, there it is. So do you see how I made all the vertical ones, which are called, sorry, axial? I made all of those ones vertical. Those are all axial. All green are axial. All green are axial currently, and all white are equatorial. Do you agree the whites come either down at an angle or up at an angle, and the greens are more vertical, up and down? All right, so let me make sure we got the naming right. So this one right here, is it up or down? Is it, it's up, yep, good. Is this one I'm touching, is it axial or equatorial? Axial, yep, yep. Okay, what about this one over here, say? Is this one axial or equatorial, and is it up or down? This one is equatorial, up. Good. And then this one back here, what's this one? Up, axial, yep. This one over here in front coming out at you, what is that one? Equatorial, and is it up or down? Not super obvious, but if I turn it sideways, you can see, yeah, it's going down. Yep. If you're unsure of an equatorial, like on each carbon, you have one up and one down. So if like my axial is obviously down, my equatorial must be up here. Or if my axial is obviously up, my equatorial must be down there. Okay, so let's see what happens when I do a chair flip of this situation. So right now, all my green are axial. Okay, they're all axial. When I do a chair flip, I take this head, make it a foot, and this foot, make it a head. What happened to all my axial greens? What did they become? All the green became equatorial. And before, all the equatorial were white. Now all the whites became axial. So when you do a chair flip, whatever's axial becomes equatorial, and whatever's equatorial becomes axial. I can do another one. Just grab any two opposite sides, it doesn't matter. Make that the head, make this the foot. And now I went back to all green are axial, all white are equatorial. Do another flip. All white are axial, all green are equatorial. So you can just switch them back and forth like that. Kind of cool, actually. I like it. It's like intellectually pleasing to see that one. Huh? So we've talked about them a lot. Oh, I didn't actually finish that last slide, did I? I didn't finish the first one, did I? Did I get to the point where I was showing the two chairs? I think the main thing I wanted to show is like, oh, you got your chair. The head of the chair is carbon 1 in this case, on the right-hand one. There we go, right? And then the foot of the chair is carbon 4. And on the other side, over here, carbon 1 is the foot of the chair in this. All right, I was just restating it. All right, then we went through that one. Okay, so I think you're getting the feel for this. I'm just gonna draw some now and we'll finish with that because I want to get to the point where when you come into lab today and tomorrow, you can practice drawing them a little bit. Because the sooner you get to know how to draw them, the better you are. Then everything's just like we're learning it right away, getting good. So this is panel 6. Yeah. So a couple of things that help.
Mark, we can't see your screen.
Oh my goodness. Could you see when I was clicking just now? What the heck? There was a while there you couldn't see me probably, huh? I'm gonna be one of those teachers who loses it in lecture. The pandemic's gotten to me. Oh, that was weird. He was such a nice teacher. And then one day the Jamboard wasn't on the video and he just lost it. All right, here we go. So I've got this cyclohexane chair. I want you to notice that these two lines are parallel. The blue ones across there. These two lines are parallel. And finally, oh wait, I should make those like different numbers maybe. These 3 are parallel. And then when you draw the chair flip, it's the same thing, but the head and the foot change. Ooh, that was an ugly one. Some of you will pick up this chair flip drawing right away. Others will be like, whoa, it's just killing me, but you'll get it. You could buy templates for this, but I think it's better to just learn on your own. All right, there we go. So let's do the same kind of thing. So this is this is parallel to that. Then this is parallel to that, and this is parallel to that. Let me see if my numbers are good there. If I go 1, 2, 3, 4, 5, 6, 1, 2, yeah, that's good. 3, 4. I was just wondering if I picked the same number of things. Okay, so now I want to draw the chair again, but I'm going to add on all the hydrogens for cyclohexane. This is just going to be regular cyclohexane. And the way you add them on is, that guy was a little sloppy. The way you add it on is I like to draw in all my axial first, and then I add on the equatorial. So I'll draw maybe all my axial in red. So I can tell for myself that this is the axial right there. It's got to be pointing up, axial up. And then on the next carbon, it's going to be axial down. It just alternates axial up, axial down, axial up, axial down, axial up, axial down. So yeah, you just keep going around the ring. And the key is you start off with the correct axial. If I would have said axial down here, then I would have been wrong on all of them. But it should look weird to you. With practice, you'll see it. So now let's do the equatorials, say in blue. So with the equatorials, they have a little bit more. The equatorials have to be pointing out from the center. So I'm going to cut this in half. This is the center. They have to be pointing out from the center, and they have to be the opposite of the axial. So if the axial's up, they have to be down, and they're at an angle. So this is an equatorial down. Oh, that was not looking pretty. Let's go. Equatorial down. See how it went axial up, and this is equatorial down. The equatorials are not quite as obvious up or down, huh? But if I were to continue for infinity, yeah, it's going down. It's getting low. It's getting low, getting low, getting low. Let's keep going low, low. All right, and then the next carbon, since I was equatorial down, I have to be equatorial up. And you notice how it's pointing out from the center, the equatorials. I wouldn't want to do my equatorial like this. That would be wrong. Or on this guy, do you think I want to do my equatorial pointing towards the center or pointing out? Center out. I want to go out like that. Oh, equatorial down and out. The next one, equatorial up and out. And then equatorial down and out, and equatorial up and out. See how they're up? They're pointing away from the middle. And I did it. I just drew on all my axial and equatorial positions correctly. And if this is cyclohexane, that means that these are all hydrogens. And if I ask you to draw cyclohexane like this and show the hydrogens, you have to write out H, because if you don't write an H here, I think it's a methyl. All right, so let me do the chair flip of that, and then we'll pause for the day. See if I can draw another decent one. There we go, not too bad. So let me start with my axial again. I'm gonna go axial up here because it seems just obvious to me. It's the axial up there. And then axial down, axial up, axial down, axial up, axial down. There we go. And then my equatorials are, I got to go out from the center. So it's equatorial down and out, up and out, down and out, up and out, down and out, up and out. And since it's cyclohexane, I got to draw on my hydrogens. I don't want people thinking those are methyls. Okay. Oh, I should number these too. Let's number it. I'll use the same numbers I've been using. So let's go 1, 2, 3, 4, 5, 6. And then I'm going to make 1 still my leftmost, 2's in the back here, 3, 4, 5, 6. There we go. So today in lab, I'll have you practice drawing these. This is a drawing skill I want you to have.